This is a potentiometer. It's an adjustable resistor. They come in many shapes and sizes. We can insert them into test boards, connect wires to them, solder directly to them, or solder them onto circuit boards. They usually have a dial, a slider, or an adjustable screw head, which lets us change the resistance of the component. They are represented with symbols like these in engineering drawings. We can use them to manually adjust the voltage or current in a circuit. When used to adjust current, we call them a rheostat. I'll explain how to use both of these later on in the video. See this game controller? Well, the joystick has two potentiometers. One measures the up and down movements, and the other measures the left and right movements. This is a servo motor. We use them in robotics. Inside, we find a small potentiometer, which is used to check and control the position of the arm. This radio uses a potentiometer to control the volume. This DC power supply uses a potentiometer to control the supply voltage. This audio equipment uses a slide potentiometer. So where have you seen them used? Let me know in the comment section down below. Okay, so how do they work? If we look at a typical rotary potentiometer, we notice there is a metal protective casing on the back, which is simply held in position by these small arms on the front. All of the parts connect onto a small brown sheet of insulation. Along the top edge, we usually find some letters and numbers. I'll explain these in just a moment. We then notice a long shaft rising up off of the device. We can rotate this to alter the resistance of the component. You'll see there is a slot cut into the top for a screwdriver, or on the side are some ridges which just help us grip the shaft. We can also attach a knob onto this. At the base of the shaft, there is a threaded section which we can use to attach the component to a sheet of material. Along the lower edge are three metal terminals. We connect our circuit to these terminals. These terminals can be straight or angled depending on the application. When we remove the back case, we can see there is a track which runs between the two end terminals. Another track runs in a loop at the center and connects only to the center terminal. The outer track has a very dark material over it. This is the resistive material. The track even looks like the symbol for resistance, so it's very easy to remember. A wiper forms a bridge between the outer and inner track. It is slightly spring-loaded to ensure a good connection. This is attached to the shaft. Rotating the shaft rotates the wiper. The further we rotate the wiper, the further electrons will have to flow to get to the center pin, and so the resistance increases. We can also reverse the connections so that we reduce the resistance as the shaft rotates. On the printed text, we usually find a K or M at the end, meaning 1,000 or million. This one shows 1K, meaning it's 1,000 ohms. This one shows 500K, which is 500,000 ohms. And this one shows 1M, which is 1 million ohms. These values tell us the maximum resistance of this component. The first letter indicates the type. B is very common. It means the resistance changes in a linear pattern. Then we have type A, which gives us a logarithmic pattern. We also have type C, which gives us an inverse or reverse logarithmic pattern. However, the letters used can vary by country and also by manufacturer. So always check the manufacturer's datasheet, or you can check the performance with a multimeter. By the way, this is the new smart multimeter from Kaiweets, and our viewers can get an exclusive 15% discount on all of their tools by using code EM15 at checkout. I'll leave a link for you in the video description. By using the resistance function on our multimeter, we can see this 1,000 ohm potentiometer has approximately 1,000 ohms of resistance across the entire resistive track. We can connect between terminals 1 and 3 to measure that, or we can measure this directly across the internal resistive material. Notice the resistance reduces as we move the probe. We can plot this and notice that at about halfway, we have half of the total resistance. This is therefore a linear B-type potentiometer. This one also has 1,000 ohms across the two end terminals, but notice the resistance changes logarithmically along the entire track. This one is also 1,000 ohms, but it changes reverse logarithmically along the entire track. Logarithmic is often used for volume control as it matches the human ear. Linear is used for things like lights or signal control. I've used the linear versions here to control the colors of this RGB LED. I'll explain how it works later on in the video, but you can download my PCB project files for free using the link in the video description. You can then order the circuit board from PCBWay, our sponsor. You just need to upload the file to their website. It will automatically fill in the options for you, although you can make changes such as the board color if you wish. Then just place your order and soon your PCB will arrive in the post. They look fantastic. We just solder the components together and we have made a simple RGB controller. Use my link to get $5 off your first order from PCBWay. They do also have an amazing shared projects library full of user-generated inventions. PCBWay also offer PCB assembly, CNC machining, 3D printing, and even sheet metal fabrication, so you can design and build anything. Do check them out, links down below. We can get these dual versions, which are basically just two potentiometers joined together. Both are controlled from the same shaft. These are useful in 2-channel stereo audio volume control. Be careful though, these have a low power rating. These can typically be adjusted 10,000 times or more. They won't fully rotate, usually just around 270 degrees. You can buy them individually or in assorted kits, depending on your needs. There are multi-turn potentiometers. They also come in different sizes and usually have a threaded section for mounting. They have a long shaft which the control knob fits onto. This is a 10-turn version, meaning the shaft can rotate 10 times. This gives us very precise control of resistance. It can usually handle slightly more power too, and this one can handle at least 1 million adjustments. You'll notice that the body is much longer than a regular rotary potentiometer. That's because inside is a spiral wire track which provides the fixed resistance. This connects to the top and middle terminals. At the center, connected to the shaft, is a slider which can freely move up and down along a conductive track. This is electrically insulated from the shaft. The conductive track connects to a circular terminal at the base, allowing the shaft to rotate. The flexible connector ensures a firm connection. The slider rotates with the shaft. The plastic slider has some ridges which fit over the resistive coil. When the shaft rotates, the ridges will therefore follow the curve of the wire, and so it can move up and down as the shaft rotates. A small spring arm sticks out from the slider and rubs against the wire coil. This also rubs against the conductive track, providing a path for the electrons and allowing us to use just part of the total resistance. This one has a wiring diagram on the case, showing the fixed resistance is between the center and right pin. The wiper is connected to the left pin. On the back, it also shows this component's maximum resistance of 5,000 ohms. Slide potentiometers look something like this. We slide the dial to adjust the resistance. They often have a flexible cover for dust protection. Inside, we have a resistive track and a conductive track. The wiper acts like a bridge between the two tracks. Moving the dial moves the bridge and changes the resistance. The 3 pins are sometimes numbered underneath, but not always. We also have 6-pin versions which have 2 sets of tracks inside. These are basically just 2 slide potentiometers joined together. There are usually some other pins, and these are just used for mounting the device. You can check the datasheet for the pinout diagrams or just use a multimeter. Printed on the bottom are some numbers and letters. The first letter tells us the type of taper. The numbers tell us the maximum resistance. This one shows 103, meaning 10 with 3 zeros after it, which is 10,000 ohms. This one shows 100K, which means it's 100,000 ohms. They do usually have a low power rating and are typically rated for at least 10,000 adjustments. Trimmer potentiometers look something like this, and they use these symbols. These are much smaller and only designed for calibrations of circuits with very occasional adjustments. At the center is a rotating part with a small screw slot or maybe a knob with an arrow. These versions have less than 1 full rotation of movement, so they aren't as precise as the multi-turn versions. I'll explain these also in just a moment. These components do have a very low power rating, so be careful. They will easily break and they are designed only for occasional adjustments. Inside we have a resistive track running between the two end terminals. A circular conductive plate connects to the center terminal, and a tiny wiper bridges across the two tracks, and this is held in place by the rotor. With this exposed version, we can see that the resistive track runs between the two end terminals, and the wiper arm connects to this and rubs along it as we rotate it. This then connects down through the center pin onto the middle terminal. Sometimes they have a small wiring diagram printed on them, but the unaligned pin is generally the wiper pin. It is easy to test with a multimeter. These small versions have a 3-digit number printed onto them. The first two are significant numbers, and the third tells us how many zeros to add. For example, this shows 101, meaning it's 10 with 1 0 after that. So it's a 100 ohm resistor, and that is the maximum resistance of this particular component. This one shows 204, so it is 200,000 ohms. Multi-turn trimmer potentiometers look like this. They usually have a small metal screw which is used to adjust the resistance very precisely. The screw can rotate many times. These vertical versions have a resistive track between the two end pins with a circular conductor in the middle, and this connects to the center pin. A wiper bridges between the two and connects to a plastic disc with gear teeth along its outer edge. The thread of the cylinder on the screw connects onto this. Adjusting the screw slowly rotates the disc and also the wiper, precisely changing the resistance. So this gives us far more precision compared to the single-turn versions. This one has a small pin diagram pressed into the case. On the top of this one, we find the numbers 102, meaning 10 with 2 zeros after that, which is therefore a 1000 ohm maximum resistance version. These long horizontal versions have a screw on the side. This one also has a wiring diagram on the case so that we know which pin is which. Inside, we find a resistive track and a conductive track held onto a ceramic base. The wiper bridges across the two and is held by a slider. Adjusting the screw rotates the thread, and that moves the slider and wiper forwards or backwards along the tracks, changing the resistance very precisely. The resistance is indicated with this number. Here, it indicates a maximum of 1000 ohms resistance. With all potentiometers, make sure to check the manufacturer's datasheet for the connection diagrams, the rated power, the voltage, the number of uses, and the type of taper. Many components will have a parts number printed on them, so you can search online and find the datasheet. You can also get an Engineering Mindset mug to help support the channel. Links down below for that. We use potentiometers as voltage dividers or current limiters. With a voltage divider, we connect the power supply across the two end pins, and the wiper connects to the center pin. This pin provides our output voltage. If we connect our multimeter to this output and to ground, we can see the output voltage varies